Pluto is a distant and confounding minor planet that was once thought to be a part of the planet family of the group of planets. Despite the recent troubling announcements made by leading astrophysicists, Neil deGrasse Tyson and Michio Kaku have delivered Pluto back into the spotlight with an incredible revelation. They suggested that this chill world is on an impact course with Neptune. Yet, how could this take place? And what might happen if this happens? Are we witnessing an important event? An intriguing eccentricity of the universe? Or is there an additional factor in this approaching limitless effect? Join us as we examine the potential outcomes of a past collision between Pluto and Neptune. The planet that was downsized to a dwarf planet is somewhat a mystery because of its odd orbit, and it remains a subject of interest and study in the astronomy community. As indicated by recent expectations from experts in the field, Pluto's trajectory is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are raising concerns about a potential risky collision between these two planets, which could represent a significant threat to the planet. This event even makes Pluto's journey around the Sun possible, unlike that of any other planet in our solar system. Requires an unbelievable 248 years to complete one orbit, which means that since its 1930 discovery, it hasn't even completed one full revolution yet. However, the fascination does not end there. The planet Pluto is identified by its astoundingly curved shape, straying altogether from the almost round orbits of the major planets. What makes Pluto's orbit even more amazing is its 17 inclination toward the ecliptic plane. The path Pluto takes is much steeper compared to other planets. One of the most fascinating regions of Pluto's orbit is its crossing point with Neptune's. For something like 20 years in each orbit, Pluto actually gets closer to the Sun than Neptune. It's challenging what we'd expect from where they are in the system of planets, which causes the logical inquiry: why hasn't Pluto smashed into Neptune? The answer lies in the effects of other objects' gravitational influences. The investigation of Pluto's orbit began shortly after its discovery. At first, astronomers tried to determine its distinct orbit from those of other planets, whose orbits are typically located close to the ecliptic plane. Pluto's orbit stood out due to its steep slope and curved shape. The mystery deepened with the realization that Pluto's orbit does indeed cross the stability of Neptune's. Pluto's orbit, in the midst of these difficulties, is evidence of the intricate nature of celestial space mechanics. The three-body problem focuses on determining how three bodies, like Pluto and Neptune, move and influence one another via gravity. Pluto's orbit is, in fact, turbulent. Minor starting condition deviations can result in substantial differences over millions of years. Despite these unusual properties of Pluto's orbit, they have been discovered to preserve stability over long time scales, especially keeping under control, according to recent simulations. These have helped us understand how the giant planets such as Saturn, Jupiter, and Neptune influence Pluto's orbit around the Sun. Jupiter's massive gravity is strong enough to keep Pluto on a stable path for potentially billions of years. These forces are necessary for maintaining celestial order and consistency dynamics. Without these factors, our local planetary system would be a place of much more unrest and unpredictability. Pluto's orbit is a remarkable illustration of celestial mechanics at play, displaying both stability and chaos, the planets in our own local planetary system, with the distinctive features of its orbit influenced by the forces of gravity of nearby planets, especially Neptune, highlight the intricate and dynamic nature of space. Predicting major events, particularly when they involve turbulent orbits like Pluto's, offers incredible challenges. The inherent unpredictability of these systems means that long-term forecasts frequently contain uncertainties. Computer simulations provide a potent means of comprehending and predicting the future behavior of celestial bodies. But they also highlight the limitations in our ability to predict. Therefore, why are prominent astrophysicists just recently raising concerns regarding a potential crash between Pluto and Neptune? Despite the various complex forces working to prevent such an event, Neil deGrasse Tyson and Michio Kaku, both renowned figures in astronomy, have expressed concern about a possible collision between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a powerful and captivating event in the planetary system. It would result in the release of an immense amount of energy, probably breaking Pluto due to its diminutive size and ice-like material. The collision could disperse throughout the planetary system, potentially posing danger to other planets and their moons. For Neptune, such a collision could alter its current setting and possibly its orbit, depending on the specifics of the crash. Michio Kaku, a well-known theoretical physicist best known for his work with string theory, provides a novel point of view to the discussion as well. His views on space exploration and the future connection between celestial mechanics and theoretical physics provide useful insights into the mysteries of major phenomena like the orbit of Pluto. Understanding the complex gravitational orbital elements and interactions of celestial bodies like Pluto can yield crucial insights for the future of space missions. This knowledge can help in navigating the planets in greater detail, effectively anticipating potential dangers, and even making plans for trips to the outer reaches. Beyond our solar system's borders, the lessons learned from studying the orbit of Pluto can be used for exploring other planets and stars, providing a roadmap for how we might approach and understand distant worlds. Regarding the physics of planets, celestial mechanics and theoretical physics are deeply interconnected. The planets' movements and interactions, including the gravitational dance between Pluto and Neptune, relate to fundamental physics principles. If Pluto and Neptune were to collide, it would be a significant astronomical event, providing an original observational opportunity that could potentially connect with string theory. String theory, theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional strings, aims to explain the fundamental forces in matter throughout the universe. The collision could result in severe conditions of energy and possible creation by gravity situations, in which predictions made by string theory may become possible to detect. For example, the high-energy impact could provide insights into the behavior of fundamental forces and particles under extreme conditions, a key area of interest in string theory. While the Earth-wide direct impact would be minimal, given our distance from the outer planetary system, the scientific implications of such an event could be profound, potentially contributing to our comprehension of the fundamentals of the entire universe, outlined by string theory and other theoretical fields of physics. Pluto's confounding dance around the sun continues to enrapture enthusiasts and scientists alike, providing a look inside the complexities of the universe's mechanics. While its reclassification as a dwarf planet sparked debate and changed our recent knowledge of planetary bodies, observations of its orbit have rekindled interest in its function in Neil deGrasse Tyson's local planetary system. Tyson and Michio Kaku, two notable voices in astronomy, have raised concerns concerning a potential collision between Pluto and Neptune, illuminating the complexities and the cosmic dynamics at play in their neighborhood. Their warnings emphasize the significance of comprehending the orbital and gravitational interactions governing mechanisms of celestial bodies. Changes in Pluto's orbit, characterized by its steepness and unpredictability, defy conventional wisdom, assumptions, and questions about our understanding of planetary movement as opposed to the nearly circular orbits of its neighbors. The path Pluto takes is unique, its course intersecting with the orbit of Neptune at points during its long journey around the Sun. The gravitational influence of other planets, especially Neptune, plays a crucial part in the formation of Pluto's orbit and preserving its stability throughout hundreds of years. Despite the ups and downs of its nature, numerical simulations of its path and theoretical models play a vital role in predicting how it will act in the future. Understanding the complex interactions between celestial bodies and planets, these simulations demonstrate that, even over thousands of years, Pluto's orbit, though turbulent, remains relatively stable within the larger context of the solar system's gravitational field. The possibility of a collision between Neptune and Pluto, as suggested by Neil deGrasse Tyson and physicist Michio Kaku, draws attention to the ongoing complexities and ambiguities in planetary dynamics. While such an event remains speculative and extremely unlikely, the upcoming gravitational dance highlights the tenuous equilibrium of forces that govern celestial bodies within our solar system. Beyond its scientific significance, the study of Pluto offers useful insights for the future of space exploration missions. The New Horizons spacecraft, which NASA launched in 2006, provided outstanding data and images of Pluto and its moons at the time of its historic 2015 flyby. The mission revealed stunning details of Pluto's surface features, like water-covered mountains, ice, and vast areas of frozen nitrogen, improving our comprehension of the geological processes that shape the dwarf planet. The success of the New Horizons mission highlighted the technological advancements and collaborative efforts required for deep space exploration. By studying Pluto and its moons, scientists gained valuable insights into the variety of celestial bodies and the environmental conditions present in the outermost parts of the solar system. These discoveries have implications for future missions to look into additional dwarf planets and trans-Neptunian objects. Helping our comprehension of the formation of planets and their evolution, Pluto's status as a dwarf planet has sparked discussion about the classification criteria for celestial bodies within the solar system. The debate over planetary classification reflects more general inquiries about classification methods used in science and the ever-changing nature of astronomical knowledge. While Pluto meets some requirements for planet status, such as orbiting the Sun and having sufficient mass for self-gravity, its classification as a dwarf planet emphasizes the variety of celestial bodies outside the traditional 8 planets. Research on Pluto's orbit expands our knowledge of celestial mechanics and planetary dynamics to the outer reaches of the solar system. By taking a look at the interactions among Pluto, Neptune, and other celestial bodies, scientists can gain further insights into the formation and evolution of planetary systems. These insights are crucial for developing theories about the origins of our solar system, as well as comprehending the processes that control how planets are formed. Pluto's discovery billions of years ago, then subsequent study have contributed to our comprehension of the migration of planets and the formation of the Kuiper Belt, a region beyond Neptune populated by small, icy bodies. Examining Pluto's orbit provides hints regarding the gravitational interactions that may have influenced the formation of planets during the early solar system. Neptune's gravitational influence on the orbit of Pluto provides an illustration of how interactions among various planets can shape the trajectories of smaller bodies over time. Future studies on Pluto's orbit and the potential for a collision with Neptune could help refine our comprehension of planetary dynamics and improve our predictions about the behavior of celestial objects. As we keep looking into the mysteries of Pluto and the outer reaches of the solar system, we might learn new things about the fundamental forces that govern our universe. A collision between Pluto and Neptune, though unlikely, would be a significant event that could provide invaluable opportunities for scientific discovery. Whether or not it happens, the examination of Pluto's orbit and its relationship with Neptune will continue to inspire astronomers and physicists as they strive to unlock the secrets of our cosmic community.